Hello everyone, in this video we are going to discuss about the decoder. Generally, decoder is a combinational circuit that changes n inputs into 2 power n outputs. The decoder is a combinational circuit that accepts n inputs and converts those n inputs into 2 power n bit output. N bit inputs is converted into 2 power n bit output. Generally, decoder is used in the receiver side. The binary information is passed in the form of n inputs line. The input is n input line. The output line defines the 2 power n bit code for binary information. The n bit line is transformed into 2 power n bit code. This is the function of the decoder. Generally, the decoder performs a reverse operation of encoder. Encoder converts 2 power n bit input lines to n bit output lines, whereas the decoder performs the conversion of n bit inputs to 2 power n bit output. This is the difference between the encoder and decoder. The first decoder is 2 to 4 decoder, 2 inputs A1, A0 and 4 outputs Y1, Y2, Y1, Y2, Y3 and Y0. Y0, Y1, Y2 and Y3 are the 4 outputs. A1, A0 are 2 input and this is the enable input. And this enable input is used to specify whether the 2 to 4 decoder is in on state or off state. The 2 is to 4 decoder will operate only when the enable input is 1. If the enable input is 0, the 2 to 4 decoder is said to be in off state. This is the truth table for 2 to 4 decoder. When the enable input is 0, irrespective of the two inputs A1 and A0, whatever may be the input for A1 and A0, the output Y0, Y1, Y2 and Y3 are 0 when the enable input is 0. When the enable input is 1, the output will be according to the input. When the enable input is 1 and both the inputs A1 and A0 are 0, Y0 is set to 1. When both A1 and A0 are 0, Y0 is set to 1. We need to just find the decimal equivalent of these two bits. The decimal equivalent of these two bits is 0. So the Y0 is set to 1. So the Y0 is set to 1. Next, for the next combination 0, 1, the decimal equivalent of 0, 1 is 1. So Y1 bit is set to 1. So the Y1 bit is set to 1. Next combination is 1, 0. For 1, 0, the decimal equivalent is 2. So Y2 is set to 1. Y2 is set as 1. Next 1, 1. The decimal equivalent of 1, 1 is Y3. So the Y3 bit is set as 1. This is the truth table for 2 to 4 decoder. Next we need to create the Boolean expression for the outputs Y0, Y1, Y2 and Y3. This is the Boolean expression. The Y3 output is 1 when enable input is 1, A1 is 1 and A0 is 1. So enable E into A1 into A0. The output Y2 is 1 when enable is 1. So E, A1 is 1. So A1 and A0 is 0. So A0 bar. Similarly for Y1 and Y0 we could generate the Boolean expression. Using these 4 Boolean expression, we could create the logic circuit for 2 to 4 decoder. This is the logic circuit for 2 to 4 decoder. Using AND gate, we are doing this AND operation. E0 and A1 and A0. This AND operation is carried out using this AND gate. Using 4 AND gate, we are generating Y3, Y2, Y1 and Y0. To create the complemented term, prime term of A0 and A0 bar, we are using this inverter. This inverter provides A1 bar and this inverter provides A0 bar. Thus the 2 to 4 decoder is realized using these logic gates. Next is 3 to 8 line decoder. 3 to 8 line decoder. It has 3 inputs A0, A1 and A2 and 8 outputs Y0 to Y7. This 3-bit input is converted to 8-bit output. This is the truth table for 3 to 8 line decoder. Similar to the previous decoder, when the enable input is 0, irrespective of the input, the output is 0. When the enable input is 1, the output depends on the input. When the enable input is 1 and all the inputs are 0, then y0 is set to 1. When the enable input is 1 and a0 is set to 1, the decimal equivalent of 0000001 is 1, so y1 bit is set to 1. For this combination 111, the decimal equivalent of 111 is 7, so the y7 bit is set to 1. Similar to the previous case, we could develop the Boolean expression for all the 7 output lines y0 to y7. For y0 is set to 1. y0 is set to 1 when all the 3 inputs are 0. So a0 bar into a1 bar into a2 bar. y4 is set to 1 when a2 is 1, a1 is 0 and a0 is 0. So y4 is 1 when a2 is 1. So a2 and other 2 inputs are 0, a1 bar and a0 bar. a1 bar and a0 bar, a2. For y7 to be 1, all the 3 input has to be 1. So y7 equal to a0, a1 and a2. Likewise, we could create the Boolean expression for all the 7 output lines. Using this Boolean expression, we could synthesize the circuit for 3 to 8 line decoder. This is the logic circuit for 3 to 8 line decoder. Using that Boolean expression, we could create this 3 to 8 line decoder. 3 inputs a0, a1 and a2. Using AND gate, we perform AND operation and generate the 4 output line, 8 output lines, sorry. Using 8 AND gates, we are generating 8 output lines, y0 to y7. This is all about 3 to 8 line decoder. Now we are going to develop 4 to 16 line decoder. For 4 to 16 line decoder, there are 16 outputs, y0 to y15, y0 to y15 and 4 inputs, a0 to a3, a0, a1, a2 and a3. This 4 to 16 line decoder can be constructed using either 2 to 4 decoder or 3 to 8 decoder, either 2 to 4 decoder or 3 to 8 decoder. There is a formula to decide how many number of lower order decoders are required. That is M2 divided by M1. M2 divided by M1. M2 is the higher order decoder and M1 is the lower order decoder. In this video, we are going to design 4 to 16 line decoder using 3 to 8 line decoder. So 16 is the higher order, M2 is 16 and M1 is 8 and M1 is 8. So 16 divided by 8 is equal to 2. So we require 2 3 to 8 decoder. So we require 2 3 to 8 decoder. This is the truth table for 4 to 16 line decoder. For 4 to 16 line decoder, this is the truth table. And 4 input lines, 16 output lines. When all the inputs are 0, the y0 is set to 1. When one of the input, that is a0, is set to 1, y1 output line is set to 1. That is, the decimal equivalent of this input is 1. So the y1 bit is set to 1. The decimal equivalent of this bit is 4, so the y4 bit is set to 1. The decimal equivalent of this combination 1111 is 15, so the y15 bit is set to 1. Now we have to convert. By using this truth table, we need to generate 4 is to 16 line decoder using 3 is to 8 decoder. Since 3 is to 8 decoder has 3 inputs only, let us give a0, a1 and a2 as inputs for both the 3 to 8 decoder. For this decoder, we are giving a0, a1 and a2 as input, and for this decoder also we are giving a0, a1 and a2 as input. This a3 bit is used as an enable. We have already seen that only when the enable input is 1, the decoder will operate. In the other case, the decoder won't operate. Just see the first half of the truth table. When the a3 bit is 0, the outputs are from y0 to y7. The outputs are from y0 to y7. y0 bit is set to y0 bit is 1, y1 bit, y2 until y7 bit. Till y7 bit the output is 1 when the a3 bit is 0. So this a3 bit is given to an inverter. This 0 when inverted gives 1 is given as an enable input for the decoder whose output is y0 to y7. Whose output is y0 to y7. Assume that A3 is 0. If this A3 0 is given to this inverter, the output of this inverter is 1, which is given as an enable input. So now this 3:8 decoder is in on state, and this 0 goes as an enable to the first 3:8 decoder. Since 0 is given as an enable input, this decoder will be in off state for the first half of the truth table, where the output ranges from y0 to y7. In this truth table, when the A3 is 0, the output ranges only from y0 to y7. When the enable input A3 is 1, when the enable input A3 is 1, the output is from y8 to y15. The output is from y8 to y15. If we give A3 as 1, which is inverted by an inverter and gives 0, this 0 is given as an enable input. So now this decoder will be in off state. When this 1 appears across this enable input, this decoder will be in on state. This decoder 3 to 8 decoder will be in on state, and the output ranges from y8 to y15. This is how we could realize 4 to 16 decoder using 2 3 to 8 decoder. Similarly, we could do this using 2 to 4 decoder also. 4 to 16 line decoder could also be realized using 2 to 4 decoder. In that case, the value of M2 will be 16 and M1 will be 4. 16 divided by 4 equal to 4. So, we need 2 to 4 decoder to realize 4 to 16 line decoder. Thank you.